Hello, hello, hello. I'm actually trying this again because somehow I streamed earlier and lost the recording. I don't know how that happened, but I also ironed out a few bugs. So I figure I'll just do it over so that our functional February kickoff video will always be here. So, what we're doing is, this is Advent of Code 2021. The very first day. It's an extremely simple problem that I want to use to illustrate the functional mindset. It's just a very simple problem that in a language like JavaScript, for example, you would just solve it with a for loop. So we have a submarine that is below the surface of the ocean, and it does a sonar sweep to find out its depth. And this is the reading that we get, is just basically a list of numbers. And what we want to do is find out how many of them in the sequence are increasing. Pretty simple. This here is an example JavaScript. This is actually solving the, I couldn't figure this out earlier, but now I realize that this is solving the second part of the problem, which we haven't gotten there yet. So basically, the whole idea is that it's a for loop. And we're initializing our counter variable at 0, that's I, and we're going to be iterating along the length of values to check, which in this step we just populated with our digits. And so then for every index, we have the first value and the second value, and we are going to compare them to see which one is bigger. And if the second value is larger, then we will increase the counter. And so that's a common way that using a loop, we would solve this problem. And when we're using functional programming, well, there are better ways to do it, actually. So instead of, all right, let's start with just a very simple input. Now, I'm in VS Code here with the Calva plugin. And this is just a regular Clojure project. And I'm connected to the REPL with Babashka, so I can evaluate things. So that's our input vector of all of those numbers. And we call input and we get them, we get it back without the commas. And commas are white space in Clojure, so it's just that they're not necessary. So it returns it without them. So we can see what we have here. And what I want to do is try to imagine how we would accomplish this without a counter. All right? Because basically when someone comes to a functional language, it's going to be kind of a mystery how to even do anything. And so I figured that this would be kind of the ideal lesson to at least solve the issue of where is my for loop? It's the most common loop that people usually reach for. It's like programming in a nutshell. Iterate along the collection, increasing a counter. So let's say we have this here. I want to be like Sal Khan and be like, I encourage you to pause this video and ponder. So here's our vector of numbers. We want to find out which one of them are increasing. So we've got the first number, the second number, the third number, and we're going to be comparing every two so that we compare it with the next one to see if it is greater than the previous one. The way to do this is by using the rest function, which all that does is it gets rid of the first element. So functional programming, in a nutshell, is about using functions and data. And that's really it. The solution, rather than the result of some kind of mechanical process, it's the output is a function of the input. So if we could somehow analyze this and find all of them that are to be compared, and this would be it here. So if we had these two sequences, then we could just compare each individual number. So the first one would be 1 and 2. And, well, we would just see which one is bigger of 1 and 2. To see whether the first one is bigger, we want to find out if, actually the other way, if the second one is bigger. So that would be true. And so we need to do that with all of these, and that is where probably the most important function in functional programming is map. So map takes a function. So let's say is something simple to we could map plus let's go to Clojure docs and find some examples for map. Yeah, so like map inc. We take the function, which is just increment, and we could do that to our input. So that takes each element and increases it, and then gives us a new sequence. And look what we have here. You know what? Hold on. Okay. So let's read this doc string again. Returns a lazy sequence consisting of the result of applying f, that's a function, to the set of first items of each collection, followed by applying the function to the set of second items in each collection. So it keeps saying each collection. And as we see here, map can take multiple collections. That is very cool. And I don't know how many, I don't know if that is a standard feature of other functional programming languages. Like, here's our example here. Map can be used with multiple collections. Collections will be consumed and passed to the mapping function in parallel. And that would take these two vectors and creates a new sequence by applying the plus function to each one of the elements of each collection. So that's how we would do this. Let's map the less than function on the input and rest input, which is just the input number is offset by 1. And here we get a sequence of Booleans. True, 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 false, true, true. That's all we need. That's the entire solution. That's pretty crazy. This is actually kind of mind-blowing. I saw this on a YouTube video. Let me show you. It was Daniel from On the Code again. And this was Daniel solving this problem. First with JavaScript, which was the answer here. And then he translated it to Clojure and used, well, just a standard loop in Clojure. So that's always there to use. It's actually, it's more of a low-level construct, and really the only time that one should reach for loop is if whatever you're trying to do cannot be done with the Clojure sequence library functions. Now, what does that mean, the sequence library? So there's, let's say we want to process this input in a certain way. And so this is what functional programming is all about. Just processing data. What would we do to this to get it into a state where it would be easier, let's say, to compare each one of the pairs? Well, we could separate them into pairs so that we would have 1, 2, 3, 4, 5, 7, and then that would be each one that we need to check. And the way we would do that would be the partition function. Now let's see how that works. So partition takes a number and a collection and an optional step and an optional pad. So it returns a lazy sequence of lists of n items each. It offsets step apart. If step is not supplied, defaults to n. That is, the partitions do not overlap. Let's see how that works. If we just did partition 2 input, and yeah, so that actually is what we want. Cool. I thought it was going to be a little bit more complicated. If a pad collection is supplied, use its elements as necessary to complete last partition. Interesting. So that's how we would separate this into pairs. Then what would we do after that? So we need to compare them. So let's say we had just 1 and 2. Can we write a function that will take these and tell us which one of them, tell us whether the second is greater than the first? So this would take A and B and I think that would be it, just like that. And so let's say I wanted to call it on 1, 2. First of all, I need to quote this list. And I need to slurp this in. Yeah, it won't take a list, it'll just take 1 and 2, like 2 numbers. There. And so what we need to do is map that on the entire collection. But what we need to do is we need to use apply so that we can apply this to the 2 digits. Right. So let's say we had the list and we wanted to do it on that. No, we could probably just use destructuring like this. No. How did they do it over here? Let's see. Yeah, see, they do have it. Oh, so why didn't that... That's the destructuring. How come it didn't work before? Whoops. Oh, because we need this entire input. There we go. So now we are mapping this comparison function over this part, the sequence of pairs. So then we're left with, well, we're left with a collection of numbers here. It's subtracting y from x. Oh, okay. This is the solution over here. So yeah, if we subtract y from x, and then filter out the negatives, then that will be just the ones where it was increasing, and then we count them. So that sounds plausible. Keep in mind that we already solved this with this tiny little solution right here. And so yeah, what I'm doing now is just showing a different way that we could have done it, with partition. And all right, so what would we do from there? We need to filter out the positives, right? filter is the other common function for functional programming. So it takes a predicate, which we'll supply as an anonymous function, where we'll just test and that should filter our result so that it's only the negatives. Yep, it just has everything except the 6. And then we would just count them. Cool. So there was another part to the problem, part 2. Considering every single measurement isn't as useful as you expected. There's just too much noise in the data. So instead, consider sums of a 3-measurement sliding window. Start by comparing the first and second 3-measurement windows. So A would be the first 3 numbers, and we add them up, which gives us 607. Then the second window is 234. So how would we modify this? Let's do that instead. So what we want to do we want to add something. We're going to add up 3 numbers. So we would take the first one of that. And then we want to add it with the second one and the third one. So what we do is process this collection just like we used rest earlier to chop the head off. That's what we're gonna do. And then to get the third one, see, there's a function called it's nx. Yeah, because that actually makes more sense to use the next function. And then the next of next gives us the third one. So we use our friend map again to map plus on these 3 collections. Oh, so that gives us our list of totals. So it takes the first of each one of these, then the second of each of these, and the third of each of these, and so on. And then we would just do the same. So yeah, these solutions here were from Borkdude, who is the author of Babashka. And I called it the "Where's the rest of the code" solution. This is like levels of tired, wired, and inspired. Is that how the meme goes? Let's see. Tired, wired meme. Wired, tired, expired. I thought it was inspired for the third one. Anyway, so the tired solution is the loop. This is, well, that's the one for the second part of the problem. Then the wired solution is this one here. So this is a threading macro, which just takes our collection and puts it through a series of transformations. And it's just it's like syntactic sugar, so that we don't have to deal with all of these nested parentheses. We could just read it down, and each it takes the collection and it threads this to the end of this list. So, in other words, partition 2, 1, input. And yeah, that's all I'm going to say about that has anything to do with syntax, and it's really just to explain to make sure that we understand what we're looking at here. All right, so if we go to Exercism, I want to do the hamming exercise. This was one of the recommended problems for functional February, and it was recommended because it is good for learning about higher order functions. What is the so this deals with DNA sequences, which are just strings of letters to represent the nucleotides. Each letter can be C, A, G, or T. And we want to calculate the Hamming distance. So the Hamming distance is part of information theory. Is the number of positions at which the corresponding symbols are different. Okay, simple enough. So the two strings have to be equal length. And this is like how we would make a I think how we would make a fuzzy search feature. In other words, say somebody misspells something in a search box, and we want to compare it to a dictionary. You know, say like all the possible words in the dictionary, but allow for one of the letters to be misspelled. Then we would match it on a Hamming distance of 1. So that's it's a very useful thing to do. And so why would this problem be good for higher order functions? Let's think about that. Because we need to compare each one. Then here it says the Hamming distance is only defined for sequences of equal length. So an attempt to calculate it between sequences of different lengths should not work. The general handling of this situation, whether it be raising an exception or returning a special value, may differ between languages. So let's look at the test suite and see the test that's undefined when lengths are different. We want it to return nil. All right, I'm going to just put a quick pin in that. Because I want to start with just a simpler one here. And so let's say we have these two strings. And we want to see if a letter from each are equal. So that's just, actually we're going to check if it's not equal, because we want to find out if they're different. And remember our map function again? If we map not equals, now this relies on the fact that we can treat a string like a sequence. And so that would be yeah, we could just take the first of the sequence and we get the character A. Or we could do a second. And we get the second letter. So let's see how this works. All right. So yeah, since each one of these is different, these two strings are completely unique. So it has a Hamming distance of 3. And so then we would do kind of like what we did before. That's kind of cool, actually, that I just happened to pick a problem that is quite similar to Hamming. So to count the trues, we can do filter identity. and then count them. And there's our hammy distance. So if I take this here and paste it in over here, this should get us part of the way at least. We're operating on strand 1 and strand 2. And we'll just go ahead and run the tests. And we got an error because we need an extra parentheses here. All right, so now, remember we had to deal with this special case if they are different lengths. So we need to return nil if they are not the same length. So let's see how we would do that. So let's say we had a function that takes two strings, S1 and S2. And we want to test equality of the count of each one. So count S1 and count S2. And all right, so there's our function. And let's say we wanted to call it on these two strings. S1, S2. Oh, yeah, what happened to my... Okay. And we have false. So there is a function, so we need to add something here that will first put this check there. And if we use the when function, then if this condition is not true, then it will return nil, which is what we want. And it should probably be it. Oh, yeah, this needs to be strand 1. And we can format this a little bit better. All right. Actually, I'm bring this up here. All right, so that's the exercise. Cool. So we learned map and filter, which are the nuts and bolts of functions. We will continue next time with the next lesson. Thanks for joining us at Functional February for the Exercism 12 and 23 challenge. See you all later.